sir.
That's perfect. Perfect. Okay. So we begin the session. I welcome all the learners, all participants. So today we are going to cover two very important topic. The first one, as shown in the screen, that is vector architecture and MIMDM architecture. And also we'll talk about the scalable, multi-threaded and data flow architecture. So let us begin this session. So in previous sessions, we have seen that how important computer architecture is because it deals with, okay, it has impact on the functional, we go back, functional performance and cost goals. And as you can understand, even human body itself, right, it's a fine-tuned architecture. So why not with computer system? So we have gone through different aspects of computer system in terms of memory, especially I have focused on memory part in terms of operating system, in terms of architecture perspective. We have also seen different levels of parallelism. What is the requirement, how it can be achieved, and what are the different pitfalls of that. And then there are different goals that we need to achieve once we are going to have architecture of a computer systems. So before this unit, that is vector architecture and MIDM architecture, we have studied about SIMD, which stand for single instructions and multiple data streams. So we have gone through in unit number 11, and with progression to that, let us go ahead with first of all vector and then MIMD architecture, followed by scalable and multi-threading operations, which we used to do with different type of processors. So the learning objectives for these two units are, first of all, recall the concept of vector architecture. We'll also have a revision of pipelining. Already we did when we have gone through unit number 6 and 7. We'll also describe the MIMD architectural concepts. One of the very important and integral part of working with architectures is multi-threading concepts. And you have might be gone through the operating system concept for multi-threading. So we'll see what's the need, what's the benefit, and what are the major principles of multi-threading. Then we'll see what are the current scalability issues. If you can remember, we have a brief introduction of computational models earlier when we started the course. So again, we'll have a recap of that and how it's going to have an impact on the various systems. And then we'll close up the session with multi-thread architectural models. So these are the learning objectives. Now let us begin with the first one, that is vectorization. So the vector architectures, as you know, and we have discussed once we have gone through the Flynn's classification. So all of you, please go through the Flynn's classification. It's very important because the majority of the topics that we have covered based on the Flynn's classification, right? So it is one of the very important concept, and it shows that we can have 4 types of classifications, right? So let us begin with this vectorization. So a vector machine consists of a scalar unit as well as vector unit. Now, a scalar processors, as all of you know, acts on one piece of data at a time, all right? And in case of vector processor, it acts on several pieces of data with a single instruction. Now, once we are going to have any vector machine, it is a fine-tuned combination of both. It may be combination of scalar, it may be combination of the vector. Although there are different variations, but according to your syllabus contents, we'll talk about the Cray-1 computer systems architecture. But if you can go ahead with more search, you can find it out that there exist many vector machines which has very components of or integrations of scalar as well as vector processors, and it varies in terms of number also. And a superscalar processor issues several instructions at a time, each of which operates on one piece of data, right? Now the scalar unit works on scalars and has architectures similar to that in the traditional processor. We have seen earlier also that it's going to act on a one piece of data, and the vector unit is responsible for performing vector operations. So this is the first slide. I wish to start with vectorization. You might have like when we have talked about the addressing mode or different type of addressing mode, we have seen that how the computation take place and how the operand can be fetched, because in previous sessions we have gone through that we can work on memory architecture or addressing mode. We can also go through memory register addressing modes. So let us try to synchronize the concept, because this unit number 11 and 13, otherwise 14 also you can say, it's just combine the basic concepts what we have gone through earlier. So that's why I referred this Flynn's classification, very important, right? Because it says now SIMD, first one, SISD, MISD, and MIMD, right? So this four classification we have gone through in different units, and let us explore much more whatsoever is remaining. Let me show you one example of vectorization. Like suppose you have two vectors. So suppose there are two vectors A and B, and we have showing vectors A is equal to say A0, A1, A2, A3, and so forth. And you may have AN minus 1. I will come back here. AN minus 1. And you have the vector B, which is B0, B1, B2, B3 till Bn minus n. So these are two vectors just for the sake of example. And I wish to perform an operation, the vector operation, which makes C is equal to A plus B, right? So the vector A needs to be added to vector B. And assuming that the vector A consists of this entire, string. This is vector B. Now, as you know that, and in the previous topics, once we have talked about this architecture also, we have seen that vector itself can perform scalar computations. So how the thing is going to go, like we all of us have the exposure to high level programming language. If you are working with C or C++, so it seems to be very easy, because we can just go through a for loop where we can have I equal to 0 and I less than equal to n and I plus plus, and we can addition of, if it is has been in terms of array, we simply write Ci is equal to Ai plus Bi, where I stand for what? The indexing of the array, or the index value of the array, or the address of that part. Now this is like which touches us. We have done so many things with compared to high level language such as C and C++ and so forth. Now as far as like the vectorization or vector computation is concerned, so how the thing is going to be computed. So you can say if I am performing C is equal to plus B, so it works like this. It's A0 plus B0, which is nothing but the basic module is divided into scalar computation. So A0 plus B0, A1 plus B1, and A2 plus B2, and so forth like this. And finally, you can have. So you can see now if you want to add these two vectors and keep the result in another vector, C. So this kind of, the operations has been shown here. And this also can be done with this. So in this case, the above loop iterates n number of times and is known as obviously for loop. So this is the scalar operations, what we did. And vector operations are defined by vector processors, what we are going through, such as only one vector instructions is required to add A and B. All right. So basically a vector instructions define four fields. And what are the fields? So if we talk about in terms of showing it in addressing modes, so you can say like this, in vector fields or vector operations can be performed by writing this kind of format. First is the operation. Next three fields can be utilized for registers. Like suppose if we have the first register V1, V2, and it's going to be stored in VR. So this is one of the component that how like we need to show what kind of operations that we are going to perform. And it says that the result of V1 plus V2 is going to be stored in this vector register. Now let me talk about, and obviously in this part itself, you can refer with different type of, like from the data from where V1, V2 is coming. It may be memory based architecture, what we have seen earlier, or there are different versions like memory registers or registers, because it has been explained so forth, right? So in this case, it depends from where we are getting, and based on the components from where we are getting it. Now, if we'll just go back to the architecture of the vector processors, so it consists of, and actually I'm just showing on the gray one. Again, I repeat, there have been much more to say, right? But due to the limitations, and obviously according to the syllabus, I'm just showing you the gray one. And the gray one consists of total, you can see 8 registers starting from V0 to V8. And every register has 64 elements. So 64 elements of 64 bits. So this can be taken as an element, and it starts from 0 to 63. So you can have this vector registers. So this total 8 vector register, as far as Cray 1 is concerned, total 8 vector register, and every vector registers can have 64 elements of 64 bit each. So this is the first part, the major component, that is the vector register. You can also have a unit known as vector load and store. All right. Third is vector functional units. There may be a integration of scalar unit as shown in that, and the last is main memory, right? So let us discuss that how it can be done. And you have also seen that in the RISC processor, RISC processor, particular load and store instructions move the vector among memory and register of vectors. So again, the pointer lies is that from where you are fetching the data. It may be memory registered, but as far as the components are concerned, so it totally replicates that how it can be implemented, in which manner it has been implicated. So let me talk about the first one, vector registers. So it carries the input and result vectors, right? So as you can see, like suppose if you want to perform any computations, so there may be vector load operations, right? Which is part of the main memory. We'll soon discuss all about this. What are the components? What are the work of all that, or the tasks they are going to handle? And one is vector functional units. So floating point add or floating point multiply, floating point reciprocal, as well as integer add, logical, and shift bits. They are going to be part of what? Vector functional units, right? Vector functional units. One unit is belong to scalar registers, and this is for write, and there may be the 2 read operations as it's required based on the instructions that you are going to do. So if I'll talk about the gray one, so every this vector registers contains 64 elements of this 64 bits each. So for example, if you just go to Fujitsu VP200 processor, it permits the space of 8K, right? It permits the space of 8K elements in vector registers programmable, and which where the range is from 8 to 256. So as 8 vector registers carry 64 of 64 bits, so but 250 registers carry 32 elements each. It totally depends on the design part. Now in this figure, you can see there are one write port. Okay, there is one write port and 2 read ports, so that the vector operations can overlap on various vector registers. And there is existed scalar registers. So vector operations get the scalar input, like suppose from this one, present in scalar registers. So if suppose if you want to perform any computation like this, b is equal to say 10 into say x plus y. So as far as this is a constant stored in scalar registers, and this x and y, they are what? Vectors. So this computations is an integration of, I can say this is scalar and as well as the vector components. Now, in case of the third one, that is which has been shown as vector load and store units. So in this case, if the data moves among memory and vector registers in this vector load store unit. So it is responsible for overlapping read and write operations from memory, because it has been connected from direct memory part itself, and also mark the high latency linked with main memory issues. So it performs load vector operation. In this operation, a vector moves from memory to vector register. And the second, let me write it also, so you'll be quite clear. So the first one is load vector, where vector moves from memory to vector register. And the second is store vector. Store vector, as you can see over here, store vector, this operations moves a vector to memory. This is the vector load or store unit. Now the vector functional unit, as I already talked about, it handles three type of operations. The first is integer operations, next is the floating point operations, and some logical operations. Now, Cray1, what we are talking about, consists of total 1, 2, 3, 4, 5, 6. Right? Cray1 consists of total 6 functional units. In case of other systems like NEC SX2, it consists of total 16 units. Let me write also. In case of NEC SX2, it consists of total 16 functional units. Okay, 16 functional units. Now, what are the 16 functional units? 4 shift units, 4 integers, that is integer add or logical, 4 FP add, and 4 FP multiply divide. So in case of NEC XS2, it consists of total 16. And obviously the main memory. So the memory unit is different from the memory unit we use in normal processors. How come? Because this units permits the pipeline data transfer to and from memory, right? So whatsoever concept we are using in terms of pipelining, so that can be very well synchronized with this main memory. Obviously, data storage is the primary element for this. But if you have seen that once we'll go through pipelining, we may have the parallel accession of the data. And once there has been any issues of hazards, what we have talked about earlier, that there may be data hazard or branch, something like, or control. So that components, which either waiting or not, it's going to be part of what? This main memory. So next we come to pipelining. And as you have already, we have gone through in unit number 4, more detail about the pipelining. So I have referred few of the slides from that component itself. Now, what is the need for pipelining? Just have a thought on this. What is the need for pipelining? Because once like we are working on, in a serial order, right? Once we are working any computation in serial order, that is serialization. And once we have the parallel computation, so you must be very clear about what's the difference. Taking any example. Now, pipelining is, you know, uh, the need rises from CPU performance, right? Because we want max to max utilization of CPU. We want maximum efficiency. I cannot claim that I can have 100% for any systems, but max performance in terms of CPU utilization and max in terms of efficiency. And we also want there should be faster execution of processes. And you have seen that one of the formula we have used, like what is the efficiency once we are working with pipelining divided by without pipelining. So that is speed of formula. We have already discussed with a numerical. And concurrency, that's extremely important, because in previous unit itself I've talked about serializability, if you can remember. So concurrency means how you can have the concurrent executions of threads or processes or tasks, the very important phenomena in the field of computer architecture. And for all these things we require pipelining concept. And system throughput, so throughput is a measurement of how many processes executed per unit of time. All right, if I just say throughput, it is a number of processes executed per unit of time, per unit of time. So obviously, as far as the process size is concerned, we require higher number of throughput, right? We doesn't want that in a single unit of time, we can have a single process running and others are waiting. So that days has been gone. That days belongs to disk operating system. We doesn't want that throughput equal to, single process at a time. So we want that more number of process. And obviously you may have a question at this moment of time. So what kind of processor you're talking about? So I'm not be very specific over here. It may be the kernel process, it may be the kernel processes or kernel threads, or it may be the user threads. Okay, it may be any of this category. But the thing is, higher the throughput, higher the system, higher the impact of the system. So this slide shows that pipelining is going to be very integral phenomena, and obviously all the modern computers that you are witnessing, that you are studying in this syllabus also, you have seen that, pipelining is going to be one of the very core concepts. And I think so that every unit we have talked about pipelining structures, how it can be implemented. So going back, CPU performance, the efficiency part, the faster execution of processes. And you can see one of the main advantages, as you can go through the literature also, you can find it out. The main advantages of pipelining is that it increases the instruction throughput, which is specified the count of instructions completed per unit of time. So obviously the program runs faster, and in pipelining, several computations can run in distinct segments simultaneously. So let me go ahead with the slide contents. And what I said that I have taken few slides from the pipelining section, what we have gone through earlier also. So you are quite, at this moment, I hope you are quite confident about instruction cycle. All right. Once any, a user issues any instructions, so instruction goes through a cycle. So if you have any instruction, it will go through a instruction cycle. So instruction cycle can be shown through 5 subtasks. The first is instruction fetch, second is instruction decode, third is operand fetch, either from memory or from registers. Next is instruction execute, and the last is write back, that is operand store in memory. So I repeat, this instruction cycle consists of 5 phases. First is fetch, decode, find out the operands, perform that, the execute, perform the executions, and the last is the result will be stored in memory. So how come this is utilized in pipelining? So I will show this. Okay, we'll come to the example in the next slide. So let us go through. Pipelining is a technique where multiple instructions are overlapped during execution. And if you remember, we have also gone through this example. Like suppose if we have instruction 1, so at T0, this gets started, but at the next time, we are, say, once this phase has been completed, so we come to the second phase, that is decode. And once in time T1, that decode of instruction 1 is there, we can have the second instruction started at instruction fetch, like this. So at time T1, we are computing. Okay, this is somehow one of the example of pipeline. And then in T2, we can see that there are 3 instructions all started. We are in this operand fetch for first, second we are for decode, and third fetch. And T3, we have the 4 subtasks. And the thing is that at the T4, the first one is completed. Instruction 1 is done. Okay. So operand has been stored and we have the output. We come back. Okay. Now, next, after every, second or every time interval, we are getting the output. In this, we are getting say this is I1, this is I2, this is I3, and so forth. So these examples we have already discussed number of times, like this. So the first instructions, it required the n phases, what's part of this, and after that, for every time sequence, we are coding the instructions that is completed. And if you can recall, we have also taken this example, a real example of pipelining. Yeah. So I have talked about a car manufacturing unit, and where suppose the car is built into phases. Like first phase deals with chassis part, the second is the body part, and the third is painting. So if you just go through one by one, so it will take the entire time. Like suppose 10 seconds, or so, I'm sorry, say it is 10 hours, 10 hours and 10 hours, so it will require 30 hours. And if you just go one by one, so one car will be in 30 hours, second will be in next 30 hours, third will be in next 30, and so forth. But is it a real condition? Is it work like this? So obviously you will say the answer is no. Once we are going through car 1, right? So these are the 3 things, right? First is chassis, body, third is painting. So it's not like that one by one. It's not like that. This is just example which has been shown. What we'll do, we'll run in parallel. We'll run in a pipeline structure. It means that if suppose the first car right now, it moves from first and second, it is in painting section. So the second car, which already completed from chassis, comes to the body repair section. And in this case, if this section is free, if this resource is free, so that can be allocated to the C3. So at a time, you can see three are operating. I'm not talking about throughput over here, that I'm getting throughput equal to three. That depends on the completion. That depends on the task completion. That depends on the process completion. That if I have an interval of say 1 hour, in 1 hour, what is the job scenario, right? Are we able to complete or not? If we can have a time, so that is a unit time that depends throughput. But here I can just say parallelly, this manufacturing unit is serving three cars. One is at this section, second is that this section, and this. And obviously you may say that resources are required. Yes, obviously we are there for efficiency, we are there for maximum resource utilization. So if we have, three people, right, appointed in all these three sections, all three are busy, and that is a real scenario. If you just go through, car servicing units, so they will not wait for that completion of one car first model has been done, they start with the second model and so forth, and in meanwhile the other car gets started. So this is the real scenario of pipelining. I hope you understood in a very proper way in the previous sessions with certain examples also. So with this, we come to just a revision definition that pipelining organizes the execution of the multiple instructions simultaneously. And if it's a non-pipeline, so obviously it's one by one, right? It's like just like one by one, and you can understand how delayed it will be. And pipelining is also called as virtual parallelism, as it provides an essence of parallelism only at the instruction level. Fine. So in pipelining, the CPU execute each instructions in a series of common steps that we have discussed in the previous case. This one. Now, if we are going ahead with certain more examples, and do remember this pipelining hazards like data hazard when we come up with the next phase of execution, but the system or that part is waiting from the data which is not available. And structural hazard in terms of resources, this is in terms of data, and this is in terms of resources where the system is going through the failure when the resources cannot be allocated as per the requirement. And control stand for the branching. You come to a branch, right? The control comes to a branch, but according to the PC or program counter, this is not available or not accessible, you can say. So this type of issues or problems we have discussed in various examples of hazards. Now we can have two types of pipelining. The first is linear pipelines, and the second is dynamic pipeline. So linear pipeline perform only one predefined fixed functions at specific times in a forward detection from one stage to next stage. While in case of dynamic pipeline, which allows feed forward and feedback connections in addition to the streamline connections, is called a non-linear pipeline. So the example we have seen earlier is belongs to the first category, that is linear. But dynamic is beyond the scope of our curriculum. So, but you may just take it point that the same way you interact with, you know, any information retrieval application, right? So I will just give synchronize with the same concept. If you have been asking to a IR application, like suppose this is a IR application, information retrieval application, and if you are just putting a query over here, now this query will get executed over here. It will have a perfect or match or ranked something results, and you can have the result over here. This is one of the traditional way of working. The second is that yes, on the same pattern you have queue, you have an IR application over here, you got the results, and again you have the relevance feedback mechanism. So this makes sense because we are not here to provide the results. We are also here for the improvement also. And who is responsible to provide the improvement? The goodness of user. User may be happy or not. It totally depends. The same happens over here also in terms of architecture things. So obviously dynamic pipeline is much better with compared to the previous one, but it has its own way of complexity. I cannot just have a tick mark over here. So do understand that pipelining may be of two types. It may be linear, which perform a predefined fixed functions at specific times and obviously in forward directions. And here it may be like this, right? It may come forward as well as feedback connections in addition to the streamline connection, that is non-linear pipeline. Now coming to the very important part of this session, that is MIMD architecture. Why is it important? Because we have gone through the previous three according to the Flynn's classifications. So this unit specifically focus on MIMD architecture, and in support of that, that's why I've just gone through unit number 12 earlier, that is storage structures. So if you just go ahead with the same concept and just try to apply with the concepts of multi-threading or multi-processing, whatsoever you know in operating system, because I hope in your bachelor's or in in few other way you have gone through understanding operating systems. So operating system is such a the theoretical concept that you learn makes sense in terms of architecture also, because once I was taking the session of the primary memory, right, especially memory, you understand that first of all I have gone through the concept of operating systems, talking about paging, segmentation, the hardware structures, the logical addressing scheme, the physical addressing. That makes sense, because until you don't understand all this concept, you will not able to understand in terms of architecture segments also. Because what is architecture? First of all, please ask yourself, what is architecture? Because if I'll talk about a building, right? If I'll talk about a building architecture, so it's not only that you are going to work with the hardware part also. You are going to managing a lot of things. Suppose if I may come up with the, itself, the world itself is example of architecture. What kind of streams are there? Computer itself. So if you are just learning the architecture perspective, don't thought that every time you are going to be functional. You need to work on different other aspects that has been taken care of the previous sessions. So when I talk about this MIND architecture, obviously, this stand for multiple instructions. Yeah, this stand for multiple instruction streams, multiple data streams, one of the very, very functional things, and multiple processors that are capable of executing vector arithmetic operations. Very important point. Using multiple instruction stream and multiple data streams. And all multiprocessing computers are MIND computers. How many of you know multiprocessing computers? Because we have talked about, and in operating system perspective also, you may have utilized this word multi in n number of things: multiprocessing, multiprocessor, multi-threading, multi-jobs, multi-program, all that stuff. So are you clear with this word multi? What is it? Okay, we'll talk about that. So all multiprocessing computers are MIMD computers. So just coming to the part that computers with multiple processors that are capable of executing vector arithmetic operations using, okay. So multiple processor, the word you must take, obviously more than one CPU. So that are capable of executing, very important point, vector arithmetic operations using multiple instruction streams. We'll see multiple instructions and multiple data streams are known as MIMD. And all this modern multiprocessing computers, they are by default MIMD computers. So it is also known as multiple independent processors which operate as a component of huge system. Now you can see that we may have the control unit, right? And we may have different instruction stream, multiple instruction streams, multiple data streams, which operating on a memory. Now again, this is a question mark. Is it going to be a common memory for all processors to handle, or you are going to have such a segment, such a division, something like that? So this leads to a new topic. This leads to a new topic, and that's a part of our syllabus that will be discussed after this. So you understand that if you're going to work with an structure or a framework of MID computers, three things are important. That first is instruction stream, multiple instruction stream, multiple data stream, and obviously the processors, right? More than one processors. Then only it's justifiable. Okay. So MIMD can be classified into two types. The first one is shared memory machines, that is multiprocessors. So multiprocessors have multiple CPUs. They independently execute different tasks in parallel. I think from the day one when we are learning this concept, that you are learning, like suppose there has been, a counter where, what I can say, like suppose you have a ticket booking counter and there is a person who's handling one by one. So this is a kind of, it's a so much delay. It's a kind of serial ordering. And if can, it can be two queue. Instead of one queue, I can come up with a second queue and I can deal with concurrent system. So at a time, this problem statement, which has been divided into modules, like suppose this has been a problem statement. The problem statement is taking a ticket and there's a person who is issuing the ticket. So this problem statement has been broken into subtask, right? Subtask like this. So at a time, in this case also, two can be served at a time, this one. So it increases, obviously this is the parallel computation, ideology what we have discussed from the day one. So multiple CPUs are required, the independent executing different tasks in parallel. And this is very important because what I said earlier, that this leads to a new topic. It may have the shared common memory or unshared distributed memories. Now, share resources, for example, input devices, system utilizes program libraries, databases, and generally it operated on integrated operating system that gives interaction among processors. Might be heard about distributed operating systems. Their programs at the task, files, jobs, so at shell level or kernel levels. So it's function, and in data element level also. That is the multiprocessor things. And we come to, from the very beginning to a very recent advancement of the multiprocessors. The second MIMD is multi-computers. So it's a message passing machines. So a multi-computers, we'll discuss soon, consists of numerous von Neumann computers that are associated with interconnection network, right? For accessing the local memory and sending, receiving messages on network, every computer on the network will execute their programs. Typically, both memory and I/O is distributed among the processors. So let us go ahead with both of them because as part of your syllabus also you must understand how it works, multiprocessors. So first of all, we'll discuss about this shared memory machines, and then we'll discuss about the different non-events machines. Okay, in multi-computers. Now, if you talk about the multiprocessors, because in the previous slide, as you can refer, we have talked about that obviously it consists of multiple CPUs, but the very important part is that how the memory segment is going to be handled. And what I said that this leads to a new classifications. So obviously this classification is nothing but the types of multiprocessors. So there are three types of multiprocessors through which the shared memory is implemented. So I must just have an asterisk over here, this shared memory concepts, and this asterisk leads to a new topic, and this topic is nothing but the types of multiprocessors. Types of although I am not very strict that this is the only way you can classify multiprocessor. There's a bunch of other techniques also, but as far as the contents that we are referring, it's three types of multiprocessors. The first is UMA, that is uniform memory access. Second is NUMA, that is non-uniform memory access. And the last is COMA, that is cache only memory access. So in the subsequent slides, I am just going to elaborate UMA, NUMA, and COMA, and let us see in terms of diagram itself. So as far as this diagram is concerned, at least we can have a starting level of understanding that if you have a multiple CPUs or multiple processors and there's a common bus, right? So you have a memory, and this memory has been shared among all these processors. How it's shared, what is the technique, what's the memory controller is going to be handled. There are a lot of things, right? So we'll discuss once we'll go through the slide of uniform memory access. And in case of non-uniform memory access, so we have a local segment of memory. Here you can see this memory is common for all. But here you can have, although I'm not saying that you break the memory and you allocate. So somehow some sort of implementation in terms of software, in terms of that, it has been implemented in such a manner that CPU is interconnected. As you say earlier, the CPUs are interconnected, okay? And they may have also a segment of local memory type of things, and which is part of that memory itself. So non-memory memory access. So this is uniform memory access, and this is non-uniform memory access. I am not showing the cache coherent part over here. That is the third one, COMA, because it's somehow related with the version of the one. So it's better you just keep in mind that if we are going to have a shared memory accessible to all, that is part of UMA, and if we are going to have the memory virtually or logically distributed among the CPUs, among the processors, that can be taken as example of NUMA. So in uniform memory access, every processors and memory modules has similar access time. All right. Now, hence each memory word can be read as quickly as other memory word. If not, then quick references are slowed down to match the slow one. Programmers cannot find the difference. That is called uniformity, right? So if because memory is, it consists of different words. Every words you may have the equal latency time or equal latency, and based on that you understand that programmer point of view, right? Sometimes we also known as abstraction. It's not find out any differences. Now, uniformity predicts the performance, which is a significant aspect for code writing. And well-known examples of those multiprocessors are NYU Ultra computers as well as General Core HEP. But this is not appropriate for scalable parallel computers, right? It's only good for constructing small size single bus multiprocessors. So what I said earlier, that it enables all processors to equally use memory chips for storage and for pre-processing. So there may be many processors in the network. Each processor is granted the same access, okay, as every other processor at the time. If you have heard about round robin kind of scheduling, round robin scheduling, I'm quite sure that in your bachelor's degree, you have gone through the scheduling of various aspects like CPU scheduling or FCFS scheduling, round robin or priority. What happens in round robin? Suppose you have processes like P, or suppose process, you have process, say this is the 5, the burst time, you have P2, which requires say 4, P3, which requires say 9, and P4, which requires of 3 burst time to execute, right? They require this much of processor time to execute or to complete the process. Now, this, for this example, what we're talking about, that uniform memory access, this is quite suitable round robin. Why? Because we have a dedicated time slice. Okay, we have a dedicated time slice. So for this example, it is 3 seconds. So what is the scenario? What kind of Gantt chart you can have? It's like this. So it depends on, if we are going to have the same structure of that, the arrive first, which will execute first. So first of all, P will execute up to 0 to 3. So this will be given to P1. That's it. Now, because it's just working on a serial order, and then we can have P2 again 3 to 6. We can have P3 6 to 9 only, right? And in P4 we execute say 9 to 12. What does it mean? It means I'm just showing you that in a linear scale, I can have 3 unit of time, which has been a common, that's round robin. So every common time has been given to each of the processor. And obviously you may ask that, Abhi, complete to nahi hua. Obviously, at first iteration, after first iteration, this 2 is remaining. Here it is 1 is remaining. Here is 6 remaining. It is 0 remaining. So again, you will have a second iteration of P1, that is 12 to 14. Then you will have P2, 14 to 15. And then you can come up with P3. P3 is the king now. P3 is the king. Why? Because 15 to 21, because P4 doesn't exist right now, it's completed. So there's a way. So that's why I just synchronize with this example, this point, that each processor is granted the same access as every other processor in the system. Same 3 seconds we have given. But this example I have taken from operating system perspective, where the process requires a CPU time. So in this model, a single memory is used and accessed by all the processors present the multiprocessor system with the help of the interconnection network. Now, each processor has equal memory access time and access speed. The next one is non-uniform memory access. So it overcomes the memory access disadvantage of uniform memory access machine. So first of all, let us have a question mark, right? And I will love to see your responses. How many of you can find it out that what are the disadvantages of this uniform memory access machine? So just now we have seen, I have just taught you that uniform memory access, how it works. We have seen the benefits also. We have seen the working also. Can you trace what are the disadvantage of that uniform memory access? So let me communicate with interact with you also. Okay. So anyone who just want to communicate about this, that what are the problems that we are, obviously I have not taught you NUMA, okay, non-uniform memory access, but any one of you, those who are present in the class or in the session, would you like to say something about what are the possible drawbacks that you understand, that you inherit from the discussion? Okay. Yes, Sudhirji. Yes, I will just. Yes, you have been allowed, Mike, and you may please tell.
Good afternoon, sir.
Yeah, good afternoon, Sudhir.
If you don't place your data properly, the distance from the CPU actually.
Okay. In terms of uniform memory access?
What I'm trying to say is it would increase the data hazard. So if you don't place the data, NUMA means actually, you don't get
Yeah. Okay. So, little bit your voice is breaking, but I understand the context you are speaking about. Perfectly said, and thank you, Mr. Sudhir. You are perfectly right that it's all about the issues of synchronization, because once you have a common memory between multiple processors, so and if you're obviously you are implementing the concepts of parallel processing in terms of pipelining, so the biggest part is synchronization. Because if you are like if you are sharing any variable, any data between multiple processors, and few other processors, they are going to write that on the same one, so how is the synchronization will take place? You have heard about in databases also, you have seen that there may be some conflicts in terms of writing, in terms of reading. The reading may also be incorrect sometimes. If you can just google it, you can find it out. There's a very famous problem known as dirty read problem. It means the processor is reading that variable, that read the value is itself wrong. Why wrong? But itself it has been taken from the memory. So a lot of things happens in terms of uniform memory access. But please have a note of this, that the biggest issue is synchronization. Although it seems to be very easy, if I will just go through implementing a small structures, so UMA is very easy, but as far as the multiple processors concept is concerned, it come up with lot of issues, lot of synchronized issues, lot of blind write issues that may be taken off, one of the drawbacks for this. Anyhow, thank you so much. I hope my voice is properly audible to you. Okay. So coming back with this non-uniform memory access structure. So it again, I will just write the biggest issues is the synchronization. It's the synchronization. Now the logical shared memory is spread between all the processing nodes machines of NUMA machines, giving rise to distributed shared memory architectures. Now NUMA machines programming depends on the global address space, that is the shared memory principles, where distributed memory multi-computers programming depends on the message passing paradigm. So soon, once we'll go through the multi-computer architecture, we'll see that how it's going to be take place for the message passing paradigm. But we'll see that how the hurdles can be removed. What we have seen in NUMA architecture, a processors can access local memory much faster, okay, than non-local memory. So this is because in a NUMA setup, each processor is assigned a specific local memory exclusively for its own use. So this reciprocate the same thing what we have discussed when I have shown you this, that each processor has its own memory. So this eliminates sharing of non-local memory, reducing delays when multiple requests comes in for access to the same memory location. So let me show you that if I'm just talking about a simple in a layman language, if there is a variable a and this variable a is equal to 10 and there has been multiple requests, okay, multiple requests of processors for these variables, no issues if this has been a R operation. R stand for read operations. But if this has been read and then write, suppose few processors wants to update this 11, this is 21, and this wants to add 51, then again there's a question mark, because if you just have a overlapping of the values, right? If you're just writing it 11, 21, so what about the values and the final value will be considered at 51? What will happen to these two values? So there are major issues that is not a scope under this curriculum, but still this is very important thing. And if you have a local memory, which we also said dirty block memory, in that we can have a proper synchronization of that instead of working in a single memory location. So before I shall move to this slide, it's better I can have few other points in terms of comparison. So you must have the clarity, okay, of I will come to this slide very soon. Let me have add one more slide over here. Let me have blank slide. Fine. So because just now we have studied very important structures of this multiprocessor, that they based on the shared memory structures, they can be uniform memory architecture or they can be NUMA. I'm not taking the third one, that is the cache model, because by default that can be understood if we can have a version of this. But because most of the processes or most of that systems which have been implemented, they have been based on this memory structure, that is UMA and NUMA. So it's better we have just learned about this, that it is based on the memory controller, single memory controller, because we have a single memory itself, and in this case we have multiple memory controller, because we have, you know, the partition memory, we have the different memory segments for the CPUs, for the processors. Now this maybe, I hope you maybe agree with this, that if we compare UMA and NUMA, right, so this is going to be faster. So this keyword faster is compared with this. Don't misunderstood that I'm talking about the remaining one also. Remaining one, once we'll talk about the COMA or the different other versions, CC and UMA, right, cache coherent. That is the different thing. But as far as this two comparison, we can say this is faster. Third one is as far as the bandwidth is concerned, because we are just giving the bandwidth to all the processors. So obviously you will say yes, it's going to be limited. But here we may have more bandwidth with compared to this. And if this is good for time sharing system, right? Though this is quite good or suitable, this is good or suitable for time sharing system, and I have just shown you one example of round robin. Okay, round robin algorithm, that is a part of scheduling from OS perspective. And in this case of, obviously it's not going to be this according to time, it's work on a real systems, right, where we require simultaneous memory access. So I can have a tick mark if anyone of you have any questions on this, that's a wish to prefer. So obviously I will say, first of all, just go through the liabilities, first of all go through the necessities. But if you're working on such a real environment, right, if you're working on a power sector, power generator unit, where the load is calculated based on the multiple inputs that you may have instantly, so obviously no one will prefer, and it's not possible that UMA can work. So obviously we'll go through an UMA, right, as far as this 2 is concerned. And in this case of obviously we have seen the slide itself that memory access is bound to be equal, right? And here it's not going to be equal. It's not equal. You may have your own, quota on this NUMA. So that's it for the first two. I hope you understood. And let me go through the next, the third one. The third is, I think we come up earlier. Okay, third is cache only memory access. Why I have taken that slide, that cache coherent, because until you don't understand this thing cache coherent, So the ideology becomes not so simple. So the cash, that's why I've taken the first two slides. Let me go back. Cash coherence, what is it? So this cash coherence scheme is a discipline that ensures that changes, very important thing, changes in the values of shared operands. Very, very important, because the operands are shared among multiple processors, right? Multiple processes, multiple threads also. So whatever changes you are going to have, that is propagated throughout the system in a timely fashion, right? I can have a very, very important part. If you have been studying operating system, you have seen that the entire working of the memory management software or memory management unit, either it is paging or segmentation, or either it is demand paging, deals with this issue, how it can be done. Also obviously there will be efficiency in terms of utilizing the memory, but this is very, very important concept. And in DVMS also, we have gone through different concurrency control protocols, serializability, all that stuff. So whatever changes we do in a shared operand, what I was showing in the previous diagram. Now, there may be of two types. The first is, write through. Okay, the first is write through. You can mention over here if it's properly visible. And second is write back. Let me show you with a clear diagram. It's not, I think, clear over here. I think this is visible properly. So if you have multiple processors, if you have multiple processors like P1, P2, and you have the cache memory. What is cache memory? The fastest memory that is very close to the processors, right? So the cache memory, you have this thing, and you have a bus, and you are using this variable shared memory. Suppose here it is the variable X. Now, if processor 1 has used this variable before update, and in case of write through, so write through means that if any update, like suppose this P2, both of them, this is shared earlier, in case both of them are using this, so this has been given to the cache, and this also given to P2. As you can see from this diagram, P1 and P2 both are utilizing this. Now after some time, after processing, suppose there has been a computation, and in that computation P2 has a change. P2 has a change of the value from X to X1. X to X1, suppose it performs certain computation over here, and the value of X has been changed to X1, as you can see, X to X1. Now what it will do, so X1 value will not be only in cache, it will be in shared memory simultaneously. So this is write through. Okay. And as you can see in this diagram also, and write back means you will do it after the completion. So processor, if any change, it will be done simultaneously, cache memory and in source memory, right? Simultaneously. This is simultaneously. So that's when you can write through. So write through means what? Write through in your main memory as well as in cache memory if there is any update. So that's what the problem we are dealing with. What is the problem? The problem is changes in the values of shared operands. So this is write through. And the write back is that the processors, if it's working with cache, the variable, shared variable, it has a change. The change has been stored over here, X1. Now, and any other, suppose any other processor wants this X, it will be given as X1, right? Like this. Now, again, you may have a thought that how it's going to be shared. So that depends on the structure we have implemented. And once it has been completed, then it will be write back to. So this is simultaneously writing in cache and memory, and this is after that, right? So I will show you through one example that may make the concept very clear. Let me have say this is main memory, and say this is a segment of main memory. We are using the cache, what we have seen in the previous example, the cache memory, and obviously cache size will be less with compared to the main memory. And then we have the CPU. We have the CPU, the processors. Now suppose if I am working with a variable, the variable is x equal to 40, right? Now say this program or the starts before, and I will show here after what happens after. Now say in that CPU there is a request of the value of x. For the value, so obviously you understand the data will come from main to cache. So here you will have x equal to 40, and then only you can see it is 40 over here. Done. So you got the value of x equal to 40. Now this I wish to show write back. Okay, I'm just writing over here write back. What will done? So just now you have studied now In write back, the things will be done after that. It means that suppose this is the computation, and the computation is say x equal to 40 into 2, right? So what in the cache it will be updated, x equal to 80. It's very simple. Here x will be 80, and that in main memory, if you are saying write back, it will be still x equal to 40, right? Meanwhile, if there is any read operation, it will take the latest value 80. Will not go through that critical section problem. Don't worry about that. I'm just showing you in terms of cache coherent implementation. So what is write back? Write back means after the completion of this, it will be written back in main memory. Now, in case of if it has been say write through, in write through, if I can have the same diagram again, say this is main memory, this is the cache memory, this is the cache memory, and this is the CPU. This is the CPU, right? So if this has been the write through, so what will happen? So in case of this, x equal to 40 into 2 done. And once it is here in cache, x equal to 80. Here also it will be updated as x equal to 80. That's it. So you can see simultaneously the value of x has been changed to 80 over here and 80 over here. So this is write through. This is write through, and this is write back. Now this concept we'll use in COMA, right? The next concept, or otherwise CC Luma. We'll see that. So cache only memory access, third one, it acts as a non-uniform but in a different manner. So it avoids the effect of static memory allocation of NUMA, what we are doing earlier, like we distributed the memory into certain aspects. And cache coherent, that is again the version which I have not talked so much of that, cache coherent non-uniform memory architecture machines. So it provides the allocation of static data, which is driven by demand to local memories. And when the data is required, you can see it always attract toward the cache memory with respect of cache coherent scheme. And in this type of structure, same cache coherent schemes can be executed as in other shared memory schemes. And they are scalable parallel architectures. So schemes supporting large scale parallel systems are only applied in this. So two things you must take. The first of all, it's going to be implemented in terms of cache coherent non-uniform structures, and there will be no static allocation, right? No static allocation that can be seen in this case of CC. Now coming to, and you can also have a note that in coma machines, same cache coherent schemes, right? What we talk about can be executed in different shared memory. It means first can be done, it can be with multiple systems also. Now coming to the second part, the multi-computers, right? The different second type of the multiprocessors. So a multi-computer consists of numerous von Neumann computers, right? It consists of numerous von Neumann computers. Are you okay with this? Von Neumann computers? I think when I introduce the subject computer architecture, so the first thing I talk about this von Neumann computers. And if I will ask you that what are the components of von Neumann? Because in 1945 itself, when the great scientist von Neumann has introduced this concept, so and universally it has been accepted in terms of showing the systems of the computers. So obviously you may be noted down this that it consists of the input, right? It may consist of the memory, it may consist of the processes, which consist of the control units and ALU, and it also consists of obviously the output devices. So they have been multi-computer, consist of numerous, and they have shown in a network. What kind of network? And for accessing interconnection network, and for accessing the local memory and sending receiving message on network, every computer on the network will execute their programs, and memory and IO is distributed, that is input output is distributed among the processors, right? So each individual processors or memory or IO model, you can see we can have a pair of three, right? In multi-computer forms in node, and is essentially a separate standalone autonomous computer with all that capacity of processors, memory and IO module. So multi-computer is actually a group of MIMD computers with physically distributed memory. hope we have the diagram also, and the day you are working with computers, hosting computers in the networks. So obviously you understand this can be taken as a framework for multi-computers. So you have an interconnection network, you have different CPUs, and every CPU processes its own memory. So it consists of numerous non-von Neumann computers, what we have discussed. And this multi-computer is actually a group of MIMD computers with physically what we have discussed in the previous slide. Now coming to the next topic, that is problems of scalable computers. So what is scalability? Obviously, one of the major focus that we want, the enhancement system should be scalable, network should be scalable. So in that perspective, obviously, when we'll talk about what I said earlier, that subsequent to this, we'll talk about scalable architecture in the subsequent slides. So there are two fundamental problems to be solved in any scalable computers. The first is tolerate and hide the delay of remote loads. As you can see over here, like if you are working with a interconnection network, so the remote load problems is that if there has been a processors which has a PEO, that is program element, so which consists of which requires the data RA and RB, and it wants the results of stored to be over here. So how in the if suppose you are working with a multi-computer environment, so how it's going to process, as you can see, so the instruction will be issued R load and R load B in this interconnection network, as you can see in the first part. And then wherever A exists, that will be taken R load and the get value of A from this PE1 or the processor 1. And the R load B instruction will be given to PEN. So obviously the main context of showing this slide is that you must understand what is the load problem, how much time it's going to be take. And then you can come up with this B value, then this value A and B, which has been obtained from here and here, it will be given to this processors, and then you can have a computation, and then it will be added. So much of delay, how it's going to be, we can have the solution for this. So tolerance and hide idling due to synchronization among parallel processes. So the very, very important issues. So what are the feasible solutions for this scalable computers? Just have a thought on this. What are the solutions? So in order to solve this, we have four proposed solutions. First is application of cache memory, right? Very important part. And you have seen also that the due importance of working with the cache coherent and other issues. So the applications of this cache coherence. Second is prefetching or introduction of threads and fast context switching mechanism of threads also. And the last is using non-blocking writes. So we come up with this four solutions, what we have discussed. Okay. The first is application of cache memory. Whatever like replication you can do in the first latency reduction or hiding method. So if we keep several copies, right? In this case, if we keep several copies of data in different location, then access from this location can be faster. So one of the thing is that replication, right? It can be faster. So this replication method is known as caching, in which several copies of data are kept nearby. Although we are not introducing the concept of distributed computing, but somehow you may just refer that also, working with different systems, and you are replicating the things, or you can have whatsoever contents that has been and I do remember that in one of the session we talk about locality of reference, where we talk about the spatial locality, very important phenomena, either in operating system or in the field of memory segments. The second is prefetching. In this method for reducing or hiding latency, what is that? The data is fetched before it is required. As you can see, prefetch, right? The data is fetched before it is required. So this method can overlap the regular expression, right? So hence the data will be in the location when the item is required. Although if you want me to give one example, I will say there's the beauty of working with any of that IR application or Google search engine, right? Although it will not be synchronized on the same forum what we are discussing, but Google works in terms of pre-processing. What is pre-processing? Whatever you may have in terms of query, whatsoever you may have in terms of information need, that is already processed, that is already ready for display. The thing is that you press enter and you have the results. That is prefetching or pre-processing. Although somehow in that case you synchronize this concept that if you search for any key term, if you search for any term like suppose Virat, so it's not like that the system will crawl and search and will give the results. That is something not phenomenal. You have that things ready, the system has ready, and you will just have a match and you will have the results. That is pre-processing. And up to that, you have heard about B tree and B plus tree. It's all about working with that, right? Although B tree and B plus tree, I'm not saying that it's used for prefetching. I'm just synchronizing the concept that how come the importance of that is. If you talk about pre-processing, so just have a thought on this B tree and B plus tree. And it's all about indexing. Indexing is what? That you are ready, that you prefetch. You have the data, you have that corpus, and you are ready for the user query. So B tree and B plus tree has been so phenomenal, so important that the industry, right? If you're working with an industrial project, you're bound to do indexing with this kind of thing. So same with prefetching also. So just synchronize that you have that operand, you have that contents earlier in terms of prefetching. Now, multi-threading, if you just go through the third one, that is introduction of threads. So this is such a wonderful concept, multi-threading. All modern computers, they have been a part of, multi-threading systems. And without multi-threading, we cannot expect the modern computers. And in case of, multi-threading systems or multi-processing systems, we have seen that context switching. What is context switching? It means, moving from one task to second task, or moving from one thread to another test. That is context switching. It's very important. So that can also be done using the threads. And the main issue is that threads are the lightweight process. It means we can have a process, so it can be subdivided into multiple threads, and we can have the parallelism, or we can have the concurrency executed through the threads also. And we can also go through the fourth one, that is using non-blocking writes. So this is the last method for reducing or hiding the latency. Latency means delay. And what is it? In this method, the memory operation, okay, starts, but the program will continue executing. But normally when a store instruction is carried out, at that time, CPU waits till the instruction completes before continuing. So you may start, memory operations, and the program will continue its executions on the case of using non-blocking write. So these are few solutions, and I have just given a brief of this, that the scalable computers issues, that how to hide the latency. I'm not going into the much more details of all these things because they have been a separate topics, and we can enumerate with multiple diagrams also. So this is just for the getting awareness that we can have some feasible solutions for this non-blocking rights, or some solutions to that. Now coming to the next topic, the main design issues of scalable MIMD architecture. So it's bit obvious that the processor design, very core concept. Second is the network, interconnection network design. The next is the memory system design and the IO system design. So these are the various design issues. So in this case, the generation which we belongs to, we are more focused towards parallel architecture features like pipelining. Okay, like pipelining, we want parallel instructions, logic issues. So we are there to build up small and mid-size multiple processor systems by providing, atomic storage units, prefetching, cache coherency, message passing. You may have nowadays, the things has so been broad that people are working in different aspect of optical computing. Have you heard about that optical computing? They are using the concept of photons. So things has been changed, in different aspects as far as the designing is concerned. Now the second one is interconnection network design. So that was a key issues in case of this was a key issues in case of data parallel architectures. So this design issues will be reconsidered that are relevant for the case, right? When multiple processors are applied to the network. So the main thing is that how you are going to handle the distributed memory segment. Third is memory system design. We have already talked about this. What are the different issues? And this is IO system design. One of the major problem, So this is a very particular serious issues when the large data volume should be moved from IO devices and to remote processors, right? If you are going to be deal with big data type of concepts in terms of IO to, you can say, the processors, so obviously it's going to be have a big hazard or hurdle for that. So how to avoid the disturbance of the work of internal computational processes? This is very important. So these are the four major concerns or main design issues. I repeat, the processor designs, because you want all that you have learned, you want all that features. Interconnection is the key issues, how the distributed segments are going to be handled. Memory, we have already talked about, you may have the different architectures of memory. And the IO system design issues, because if you are going to handle a big amount of data, so how the things are going to be executed properly. So with this, I have discussed, few very important topics related to the first part. And you may have heard about the things like CC, NUMA machines, or COMA machines, or load memory data, or data diffusion machines, or massively parallel processes. All these things are very important. Just have a note of this, because these things are going to be, a very important trigger for many others issues of, computer architectures related to. So because in previous case, we have talked about, let me show you that I come to the second part, and in this, it's extension of the previous one. So this belongs to your unit number 13, that is scalable, multi-threaded and data flow architecture. And let me go ahead with the very initial topic of multi-threading. And for that, it's very much required about the threads. So I love to have this topic again, because in my previous session also, OS perspective, once you are learning the threads, please focus your attention in terms of operating system, because operating system has been the key factor executing the threads, right? So multi-threading is the ability of the CPU to provide multiple threads of execution concurrently. A very important thing. You are executing what I said, right? That you may have two queues, right? And they are serving two people. That can be taken as one of the thread examples. Two threads serving simultaneously or concurrently. So multi-threading enable us to run multiple threads concurrently. Very important, very phenomenal, very practical topic. And you can see in the example, for an example, in a web browser, one thread, the first thread handles the user interface, okay? And the second thread, which fetches the data to be displayed. It means you are just filling the data in a form, and you're also getting some responses from the backside. So there are two threads which are active. So I wish that you have a basic understanding of thread, but I have also included few slides from my previous you know uh, seminar, where I have talked about the thread concept. But let me have a very brief recap of all that. That says, if we define the process, so the things start with program. So program, generally we say it is in non-volatile memory, or it is in secondary memory, the piece of code, right? The piece of code that has been written in that secondary memory, that has been stored or saved in the secondary memory, that is program. And when program comes to main memory, okay, when it comes to main memory, it is a process. And that's why we say this is static, this is dynamic, okay, because it's sleeping and it's executing. So a program in execution is known as process. You can have this definition, very important, that process is equal to program in execution, and the execution of a process must progress in a sequential fashion. Now, what is thread? So entity within a process that can be defined as a lightweight process, lightweight, lightweight process. So that can be scheduled for execution. So this is a basic unit of CPU utilization, and consisting of a program counter, stack, and a set of registers. And each process is begin with a single thread, that is a primary thread, and it can create additional threads. I'm not going through that perspective, because thread itself or process itself is a topic of another 1 or 2 hours. So we'll not go through that. It's just a recap, that if you are learning this topic multi-threading, so you must understand the different so and go of this multi-threading. Okay. And I'm also sure that you are okay with the concept of multi-threading and multi-processings, all the things, right? So the basic difference between process and thread is that every process has its own data memory location, but all related threads can share the same data memory. Very important statement, right? Threads can share share the same data memory and this process, because obviously process comprises of different threads, so they can share that the same memory that the process have. And I have also talked about process control block for, but I can skip it now because we are more towards multi-threading. As you understand that PCB stand for process control block, which consists of different elements like the pointer, this what are the states. You may recall that there are 5 states: new, ready, running, waiting, and terminated. Okay, process number, counters, registers, what is the memory requirement, what the file it has opened. So this is PCB we have talked earlier. Okay, this is process state diagram. I think I can skip this. New, ready, running, terminated, and waiting. They are the 5 states of process. If anyone of you have missed the class, I will just remind you that when it enters into the memory, any process, it is in new state. When it is in this queue, ready queue, right? It means that now the processor can pick any of that processor which are in ready queue, and once it may go ahead with once any of the process can be taken, it will move to the running state, like you can see here. Now running means it's a limitation, only one process can be in running state. And it can also, if there is any interrupt, it will move to waiting state. After the waiting is clear, it can go back to ready. So this ready is a state where it maintains a queue of all the process which are ready for execution or running. And finally it's get executed or terminated. So this is the process state. Now thread can be single thread or multiple thread. So one program counter and one sequence of instructions at specified time. And in case of multiple threads within a single process, we'll have own program counter, stack, and set of registers. Let me show you through diagram also, as you can see. So it's a single threaded process. It consists of code. What is the part of PCB I have shown? Data, files, stack, registers. And if it is say multi-thread process, so it will have its code, registers, and stacks, right? And data is going to be common for all. So this is a single versus multi-thread example. And I think I have shown this earlier, concurrent execution. Like suppose if there's a single CPU and it has different processes or threads. So thread 1, so one CPU is working over here. So it can have, after once there's a gap of this is a delay. So at that time, it will serve the second thread. Then it will go back to the next one and so forth. So CPU, the thing is that it's going to be busy all the way. We have utilized the processors. Now we have also seen the scheduling policy. Let me have a photo. So I'm just skipping this part because we have gone through earlier that if we have multiple CPUs like this has been shown, so we can execute 2 threads at a time. That is the parallel execution, what's the main core of the entire things, and we can have parallel concurrent execution also. So you can see there are 2 CPUs and they are serving two tasks every time, right? So we are utilizing the max of max. This is free. Second thread is active. Here thread 1 is active. And not only in this CPU, second CPU also serving like this only. 4 tasks they have been served at a time. And this is the Flens classification. We have just gone through the MIDM. So these are the few old slides. I have just referred that for this. Okay. Now we come to the part of benefits of multi-threading systems. So a lot of things because a process has been distributed among multiple threads. Threads can execute concurrently with the same data state with their own internal functions of registers and all that. So let me explain all these things. So they advance the communication, right? That's why I mentioned better communication among inside the processes. Different execution traces, user address space is shared. Once you will use the throughput, so obviously throughput will be increased if this has been efficiency measure. So multi-threading improves throughput. You will have superior application responsiveness. It means that we have, suppose in a corner, application 1, application 2, application 3. Application means user interface you can consider. So you will not wait for the entire duration. Okay, you can have a better responsiveness. Response will be better, right? So like this. Improved server responses. You may minimize system resource usage. Program structure simplification, okay, because There's a piece of code that has been, divided into threads, and this is going to be concurrently execution. Although there may be some synchronous issues, but it's going to be have a faster responses also. Now, what are the principles of multi-threading? So there are a few important things which has been listed over here. Let me go through one by one. The first is number of threads in each processors. Let me check the timings. Okay, fine. So number of threads in each processors. First one, why this is coming? Okay. So this number of threads in processor, it specifies what? It specifies the level of parallelism. It specifies the level of parallelism. So it can be in computation parallelism or communication parallelism. What is computation parallelism? So communication parallelism is the means by which threads can correspond with other threads existing in other processors. So this is very important thing, that in the level of parallelism, you may have, it decide that how many threads you are going to have in each processors. The number of remote reads in each threads, very important thing. In a single thread, how the other processors that are reading, okay, that may have a read operation. The context of switch mechanism, right? Because you have seen the context switch, right? So context switch has been a very, very important issues once you are going to work in a multi environment, right? Suppose I will show you through one example. If you are going to have handle this thing where P1 is executing and the control moves to some other processor P50. So what kind of, timing that will give for context switch? This is a very important thing that needs to be handled. And there are different modules of operating system that they deal with this. The remote memory delay, right? Remote memory serving mechanism, and number of instructions in a thread. That is also going to be a very important part of this. Now, if you have heard about this number of instructions in a thread, so it depends on the granularity. And this granularity can be divided into fine grain, it can be fine grain, it can be medium grain, or it can be coarse grain. What happens in fine grain? It's a thread of few to 10 of instructions. It is basically for instruction level multi-threading, the fine grain. The second, we have gone through the medium grain, and the next is coarse grain. And it's all about the granularity. It increases like this only. So these are the few principles. I repeat, the number of threads matter in each processors, number of instructions in thread, and the remote memory latency, the remote memory servicing mechanism, and the very important, I have especially focused on the context switch. The next topic is scalable and multi-threaded architecture. So let us go ahead with the first part, that is scalability. So I think in computers or in information technology era, we doesn't come up with any of the system which should not be scalable, because, and as far as like in a very layman language, in any terminology, scalability has been given due importance for every aspect. What is this scalability? Scalability is all about enhancement. It's all about addition. It's all about advancement. So in terms of computer architecture perspective, scalability is the skill to enhance the amount of processing that can be done by adding up further resources to a system. And it handles, is the property of a system to handle a growing amount of work by adding resources to the system. And we want that all systems should be scalable. That's major issues. So what kind of architecture we must have? So a computer architecture that is designed to execute more than one processors is called a scalable architecture, obviously. And all business applications are scalable, even if you have heard about 2-tier or 3-tier architecture. So they are all scalable things. Any moment of time, if you want to increase that, if you want to add up in terms of any of the resources, so they must be ready to adapt that. And it's not like that you are just getting in terms of hardware structure. In terms of controller also, they must be achieved that. So scalability can be achieved in several ways, such as using more CPUs or adding extra CPUs. Now, two very important terminologies of scalable architecture. I hope you may have interacted with this earlier also. Scaling up and scaling out. So what is scaling up? So scaling up means add extra resources to a single machine, right? Add extra resources to a single machine to allow an application to service more requests. So it means that what kind of resources? It's all about resources. So what are resources? You may have extra memory, you may have faster CPU, you may have higher bandwidth and so forth, right? So this is scaling up. And what is scaling out? So now you are adding the servers to a server group. That is scaling out. You have more and more servers. Although if you know about this earlier, because scaling up and scaling out, this is not in the first time I'm introducing to you. You may use this in context of very other definitions also. So don't combine everything what you have learned earlier. Scaling up, scaling out in terms of this scalable architecture I'm talking about. There are other terms like scale up, scale down, scale out, scale in, but we are not into that. Okay, just this two term perspective in terms of scalable architecture. Now, computational model, that's the next topic that we wish to discuss. So the computational model determines how computation will be programmed and executed in a computer. And if you remember, when we started the subject in the very first seminar, we have discussed about this computational model. So it's composed of an architectural model of a system and the programming language. So this is the abstraction, okay, of what the architectural part of the system as well as the programming language, which are written in programs. And the corresponding architecture and language classes must have a common foundation on paradigm called a computational model. It's such a important topic, or I can say if you have heard about mathematical modeling. So just have a thought on this both. Can you differentiate between computational model and mathematical model Like suppose if I talk about the Turing machine, I say Turing machine is equivalent, right? Is as equivalent as capable as computers, right? I'm not talking about in terms of architecture perspective. I'm just talking about as mathematical modeling is concerned, whatever computers can do, that can be very well modeled through Turing machines. How it can be? Now again, you have a question, sir. आपने तो कभी सुना नहीं है what is Turing machine? So if you have gone through the context of like working with Turing thesis, because this has been phenomenal, and nowadays people are working on deep Turing thesis also, deep Turing machines also. Such a phenomenal concept where in computational terminology, what I can say in computers, if you want to write a program, if you want to write a C program of say factorial, what you will do, you will start with simply void main, and you will start coding, and you will do recursion, whatsoever you want, you will just code over here. You will have a piece of code in high level language, right? But this is a computational model that you're going to program in terms of Turing machine, right? How come you're going to justify that you will have this factorial? You need to have a like suppose if I can show like this is a machine which acts like this, and it is the final states. So this machine shows that you can capture any expression like a, and this is somehow is shown as what the mathematical model. Also, I will not go into the brief. So the mathematical model, you can Google it also, Turing machine, and the computational model is that how we are going to program in terms of other perspective. So this, there are three types of computational models. The first is the von Neumann model. The second is the data flow model, and the third is the hybrid multi-threaded model. Okay, so there are three models that can be taken as the computational models. So we have talked about this earlier also, that the computational model which links the computer architecture and the language groups can be very well abstract with these three components: the basic items of computations, and the problem description model, and the execution model. Let me show you in very brief. First one is this basic items of computations. So the requirements of the item to which the computation is referred, and the sort of computations that are executed on them. And okay, yes, I just forget that Turing model is there. So Turing model, or the von Neumann model, and the data flow model stand on theory of data. Very important phenomena. Although we haven't restricted, but I love this topic, Turing model or Turing thesis or deep Turing. You may find it out how relevant it is nowadays. So coming to this, the von Neumann model, I think the first category that I said, that are three computational models. The first computational model, and this is the first von Neumann model. What earlier also we have shown, or we have discussed. I think we can discuss in very short, because we have discussed von Neumann model, the basic model of computation, number of times. So what are the components? The components of the von Neumann models are, obviously the components is the input from where the data will be taken, the input, the second, Let me show you here. Yeah, the input. Second is the memory. The memory. Third is the process. The process, which consists of control unit plus ALU, that is arithmetic logic unit. So this is a process part, and third is output. So this has been given by okay. So please let me know I'm audible. Anyone of you can please raise your hands that I'm audible. Okay, okay. So thank you, Sudhirji. Thank you, uh, Tushar, Arshi, Abhishek also. So thanks to you all. Thank you. Sorry, there was a disturbance, and now I continue. Right. So I was just talking about this von Neumann model that it consists of input, output, and that the process part, the processor, and the memory. That is a von Neumann basic structure. So once the input will be provided, first of all, the input, it will move to the control unit, that what kind of operation it is. And then it will instruct to ALU, from where you can have the memory part, the data. And once it is executed in, ALU, it will be given to as output, or in terms of your printer or your monitor, that is output part. Okay. So do remember that very important and very integral part. Now, I think I can skip this slide, because if you can just refer the recordings, we have discussed all these things in our first unit, okay, in first webinar. Execution models, we have also discussed about all three stages. Yeah, so I come to the next topic, that is the data flow architecture. And if you want to refer any of that part, the program model, execution model, we have already discussed in the previous case. So a data flow graph is a graph model. It is very important, because number of times describing computers, we have used the flow charts and other modeling techniques. Even if, while teaching databases, I love to go through DFD or ER diagram, very important. So this is the data flow diagram, is a graph model for computer programs that express the possibilities for concurrent executions of program parts. So control and data aspect of a program are represented in one integral model. And there are four possible options for executing instructions. The first is the control flow method, right? And traditionally we are working with this only, control flow, the program counter. So an instruction is executed when the previous one is in defined sequence has been executed. This is a traditional way, right? The same way we have incremental program counter values. The second is demand driven. The second is demand driven. So its instruction is executed when the results of the instructions are required by another instructions. That's the demand driven. The pattern driven, an instruction is executed when particular data patterns appear, right? If we can have a pattern like this, okay, then only we can have, suppose this is the pattern AN and BN. What is the pattern? A to the power and B to the power. This is a pattern. So once this, we can have any pattern in, I'm not limiting myself to this kind of examples. You can just go through any encryption or decryption issues. When we have that kind of patterns, then we have this method. And the next is data flow method. An instruction is executed when the operands required become available. So these are the few mode where we work. And data flow architecture is a computer that directly contracts the traditional control flow. That is the von Neumann architecture. It does not have a program counter, and the execution of instructions is solely determined based on the availability of the input arguments to the instructions. So I can show you that in case of data flow programming, what you also refer in the notes provided to you all, we have this data flow graph, which I will show in the next slide. You have the library of different functional bodies. There may be control generator, like this is the part of where we need to start. And once we have the control software, we can have a runtime supervisor. So you can see there are two modes. The first is starting and second is running. This is one of the model which comprises of different elements. And in this case, you show the computational component through the node, arrow is used to show the buffered data channel, and the control algorithm is divided into node first. Let me show you the next diagram. Okay, that will make the things very clear. So you come up with this kind of data flow graph. If you have any idea about the data flow diagram, DFDs or ER diagrams, and you want to see the data flow So this data link, you may have this diagram. This is just a notation we have used in case of data flow diagrams, as it's very clear. And you also gone through the dynamic critical path of data flow graph simultaneously with different program dependencies. So what I can show here, that this is for use data link. You can see the solid field over here. If there is nothing like that, it's a space or blank, it's a control link. You can show through operators, this true gate or false F gate. You can also show through the merge operation, or it's a decider, where this is taken as a logical one. So this is, if you can remember, like suppose if you use this decision block in the flowchart method, where you have certain inputs, which decision to take. Same over here, like decider, you have certain signals, and this P is predicate, or which is decider. And if you want to merge this two, you can have the other options. This is such a notations. I'm not going through the definition. There are different simulation tools also. If you want a session on this, definitely we can take a simulation based taken session on this data graph, and you can simulate various aspect of programming. If you are interested on this, I request you that you may refer any simulation based data flow graph available, freely available in various aspect in systems, and you can work on that, and you can design some sort of data flow graph for any architectural issues. So with this, we come to the conclusion of the session. We have discussed about the MIMD architecture. We have discussed about the various parallel architecture. Apart from this, like suppose like the data flow model and the one human control flow model that we specially discussed in the previous one, there are few other things, and that may also trigger to what are the changes that you may have. That will be beyond the syllabus. If you can take one by one, so I have just listed over here that you come up with this McGill data flow architecture. If any one of you are interested, definitely you can have a better understanding in terms of, first of all, you need to search on this key models, P risk and star T model. And there have been few very important papers that I have found out, and I have read that also, so that I have listed over here. If you can just have a Google on this. So the first paper given by Guang ETAL, that is hybrid technology, and this is taken as the state of the art paper, that hybrid technology multi-threaded architectures. So you can just refer, it's a PDF is available. You can just find it out, and you can refer if you want more the things, because many of the concepts I have seen, they have been integrated and implemented in this PRISC and LNC model also. And the second paper that come out, very recent paper I can say, that is in 2019, that is the Journal of Supercomputing. So the paper is a hybrid sample generation approach in speculative multi-threading. So this is very another important paper, and if any one of you is interested to enhance your knowledge on this subject and to have a more advanced level of understanding in many of the new things which has not been covered in the syllabus, so you may approach I think these two papers. These are very important. I think the first paper is state of the art paper, you must go through if you're interested, and the second seems to be some research pointers if you wish to be have some sort of, because people are doing so many things, like suppose cloud computing, people are working about different issues on that scalability. One of the issue is cloud computing. So why not to mold yourself while working with the scalability issues with computing and other aspect of architecture also. So with this, we come to the summary part, and I hope in this unit we have learned about the vector processor concept at the very beginning level. We have also discussed about the MIMD architectural concepts. I have focused, and it's a kind of revision for you people, multi-threading. We have seen the need, benefits, and principles. We have also discussed the scalability issues and the various computation model, which are going to be first and second. First, non-Newman, we have discussed. And if you want more, you can refer my contents of the starting first or second webinar. And in last, we have discussed about the various multi-thread architecture models. So with this, I conclude. Thank you so much.
Thank you. Thank you, sir. Thank you, everyone. Sir, there are few questions from the learner side, so please address them.
Yeah, please tell me. Arshi, please tell me. Okay, wait. I will just go through. Yes, Arshi, if you have any question, you may please ask.
Good evening, sir.
Good evening, Arshi. Tell me.
So, explain one more time what is DFT?
DFT.
Yeah, sir.
Yeah. Okay. So actually, Arshi, DFT, I have just referred with one of the synchronization level, but it's not be very specific with this part. But because you are asked, so DFT stand for data flow diagram. Data flow diagram, and this is particularly used to show what is the flow, what is the syntax of the entire data that we are going to handle into the system, right? Into the system, right? So like suppose for an example, if you are getting say data from two nodes, right? So I can just show that you are getting the net data from two nodes, and suppose you have built up an application where these two incoming nodes, right? This arrow shows the incoming, so this is node 1 and node 2. And if you have any sort of say operations, and this operation is going to be part of these two nodes, then I can show over here. So actually the thing is that I am not towards more into the symbolic notation. Data flow diagram is that if you are going to build up any application, so what is the flow of data that you are going to have? Not in terms of only system perspective, in terms of your suppose if you have heard about two-tier architecture or three-tier architecture, so in terms of that also how you're going to handle. So for an example, if this has been database server, so here you perform this, DFD says that you have this part over here, and then you come up with some other things. Like suppose this data is going to pass in some other part. So that is the data flow you may have. But for more explanation, I request you that you may just search on Google itself. So you may find it out the various components. But in the very layman language, I can say that DFD is one of that type of visual representation which follows or which shows the data flow in the entire system or the entire network that you're going to have.
Okay, sir. Thank you.
Yeah, okay, thanks. And particularly, Arshi, this DFD can be taken as a part of software design. Okay, because once we go through the UML diagrams, so it is well supported through DFD also. And if you go through the ER diagrams, that is more supported towards the databases part. So if you have been any subjects like software designing, you may definitely come across the data flow diagrams and UML diagram also.
Okay, sir.
Yeah. Okay, so Panduranga Rao, yes, you will be. I think your mic is on already.
Yeah, I just raised my hand earlier when you asked me to check
Okay,
whether
okay,
I'm audible or
okay.
not. Yeah,
So first of all, thank you, Panduranga, for being in the class and being a very active learner. Thank you.
thank you, sir.
And is there any other question?
Hello.
Hello.
Yes, sir. Abhishek this side.
Yes, yes, Abhishek. Good evening.
Good evening, sir. Sir, my question is, what is the difference between right back and right through?
Okay, okay.
Yes.
Okay. I've shown you one example, Abhishek.
Yes, sir. Yes, sir. But in that case, in right back, the data is written in 40, but in right through, it is stored in case.
Yeah, yeah.
In
See,
that case, yes,
yeah,
sir.
yeah, sure, sure. I will let you know through this right through. So in right through, what happens? Like suppose actually, see, this is you know we are working on CPU level, right? And you have the cache memory and you have the main memory. What is the normal flow? See, I can also include the secondary memory. So the normal, this is the biggest memory in the terms of hard disk. The flow is that from secondary to primary, the data comes. If you say suppose x equal to 100, so this value is permanently stored over here, x equal to 100. Now suppose I am a user. As a user, I just want I need to do something. So I'm saying ki I want x because x is my balance and I want to withdraw some amount. So I have just asked this to CPU, give me what is x. What is the value of x? So tell me what will happen. So the value of x will move from secondary to main, from main to cache, right? And cache to CPU. The way can be shown. So every time this x will have 100 over here. Okay. Now in cache also it will be 100. I'm sorry, this is 100, and here also it is 100, and the user is quite happy to know that my balance is 100. You got it? Now suppose I just want to add 400 rupees more. That's it. 400 rupees more. Okay, so this is total is 500. Now because this is a computation, right? What is the computation? 500. Now in case of write through, what will happen? Simultaneously this value will be updated over here and over here, right? Not here. This is when we save, that happens. So 500, because right now both of them have 100 now. So in cache also this will be 500, and here also this will be 500. That is the main logic, right? So simultaneous region, that is write through. And once we save the entire thing, or once we have the write operations, something, it will be stored here also 500 later on. So this is the logic. In case of write back, see, this is just a mode of computations what we are doing. So in case of this, if 500 has been done, so in cache memory it will be updated as 500, it will be done. But in main memory it will be still the older value 100. You see the difference here, both are same, here both are not same. Now you may ask me, sir, what is the benefit of this? The benefit is that if you have some more computation, like suppose if you have some other things, everything is going perfect. This is a separate block, which is itself, it's a part of memory. Now suppose you have changes 500 to 600, it's okay. 600 to again 150 is okay. Then 900 is okay. Whatever changes you may have over here. And at last, like suppose you end up with the value 950. At last, when we are going to write the final value, or this is going to be log off, this 950 will be changed over here. Nothing is, no harm is there. Nothing is going to be missed. You want 950, and once you save the system, it will be stored as 950. So this write through means it's a parallel writing, simultaneously updating both, and write back, you are updating only cache memory. At last you will update the main memory value. You, not only you, it's a system part of things which has been implemented. I hope I have answered your query with one of the example.
Yes, sir. Yes, sir.
Okay, fine. So thank you for this question itself. And I think I have handled RC, Panduranga, and Abhishek. So thank you to all for being so active, so good, so nice learners. I wish you all the best, and I over to ma'am.
Thank you, sir. Thank you, everyone. If still you have any doubt, please put it on the discussion board. Thanks, everyone. Have a nice day.
Thank you.